Welcome to the today lecture. Today we like to cover this power quality standards. We discussed little bit about last lecture about the different power quality standard. There are large number of standards, but the most important standard which are widely referred around the world is from IEEE, 519. This talks about current distortion limit for general distribution system for the 120 volt to 69 kilovolt supply system, and most of the loads normally in distribution system, like in India also we have supply system 220 230 volt, it comes in this category, or 415 3 phase system. So, all comes under this category, and this is the maximum harmonic current distortion percentage of the load current, that is IL, and these are the individual harmonics, which odd harmonics. And well, if we look into the first row, that is ISC upon IL, that is a short circuit current level divided by load current, up to 11th harmonics, and then second limit is 11 to 17, then 17 to 23rd, 23rd to 35, and less than 35, and total demand distortion factor. And this total demand distortion factor, of course, we discussed last time, it defined in terms of the nominal current, like. Well, you have this complete table, and if you look into on the left side, the first row, the short circuit current level is given like a 20%, means that your source impedance is typically a 5%, means like it is a 20 per unit, means 5% is the source impedance, it means 1.05, that is will be equal to 20. So, it means your source impedance is 5%. If source impedance is 5%, this is the percentage level of harmonics can be afforded, and maximum demand distortion factor in the load current can be 5%. But if your short circuit current level or source impedance is lower, like 20 to 20 per unit to 50 per unit, like 50 per unit means you have a source impedance 0.02 per unit, then in that case this distortion can be permitted little more, like maybe 8%. And in the table, if your source impedance is typically when short circuit current level is the 1000, means your source impedance is 0.01%, 0.001%, then you can think it is allowed 20%. The reason being that if source impedance make a voltage drop corresponding to those harmonics, so voltage distortion also should not go more than particular value. And even harmonics are limited to 25% of the odd harmonic limits, and current distortion that result in a DC offset, like similar to like a half wave rectifier or half wave converter, are not allowed, and all power generation equipment limited to the value of current distortion regardless of your actual short circuit current level, where the ISC the maximum short circuit current at the point of common coupling, and IL is the maximum demand load current, that is typically a fundamental frequency component at point of common coupling. Well, this is the typical limit corresponding to the voltage when we have a current distortion limit for general distribution system of 161 kV, for dispersed generation and cogeneration. It means you can understand the voltage level for 161, more than 161 kV is certainly either at typically maybe at primary distribution, or it can be transmission level also. So, there the harmonics level permitted much lower, like there even for short circuit current level of even less than 50, it is permitted only 2.5%, and well, if its short circuit level is above 50, then it is allowed 3.75. So, there is a more strict line, and we never we do not expect at such a high voltage level you have a really large distortion, like So, that is the table divided corresponding to the voltage. This is the table, interesting table for corresponding to the voltage distortion limit, and this also indirectly guide the previous table also. So, here you can call it like a the bus voltage at point of common coupling, if it is 69 kV or below, the individual voltage total harmonics distortion is not permitted more than 3%, and total voltage distortion not permitted more than 5%, like. So, this is the limit which guides virtually the previous case which we discussed it, and if it is 69 to 161, then it is individual harmonics permitted is 1.5%, and total voltage distortion permitted 2.5%, and if it is 161 kV and above, then it is individual harmonic permitted 1%, and total harmonic distortion not more than 1.5%. So, typical example may be high voltage DC system, can be up to 2% total distortion, where the cause is an HVDC terminal that will attenuate by the time it is tapped to the user like. Well, there is another shunt we discussed last time, it is IC 61000, and there were several parts in this standard. So, this is the one typical table which is very widely used of 61,000 IC 61000. IC that we discussed last time, International Electrotechnical Commission, 61000 3.2, the maximum permissible harmonic limit for class D equipment current limited to less than or equal to 16 ampere per phase. So, this all the single phase, you can call it the equipment, because most of the time you might have a 16 ampere socket on your typically a power socket we call it. So, all the equipment connected in distribution system is governed by this table. These are commercial standard we discussed last time also, developed in Geneva, this International Technical Commission typically installed there. And the harmonic order here you can see third is permitted corresponding to 3.4 maximum harmonic current per watt. So, this is in milliampere per watt. Okay. So, 3.4 milliampere per watt, and the maximum permissible harmonic current permitted 2.3 ampere. Similarly, for fifth harmonics you have a 1.9 milliampere per watt and maximum is permitted 1.14, and seventh harmonics typically 1 milliampere per watt, and typically maximum is harmonic current permitted 0.77, similarly 9.5 milliampere per watt, and the total 0.40, and similarly 0.35 and maximum permitted 0.33 ampere. And all the harmonics 11 to 39 odd harmonics, they permitted 3.85 by H, where H is the order of harmonics milliampere per watt, and certainly the maximum permitted 0.152 divided by H, like order of harmonic. So, this milliampere per watt means you might have like a 100 watt equipment. So, certainly these quantity will be multiplied with the 100. So, this is with the IC 61000 like standard like. Similarly, IC 61000 to dash 2 is for voltage distortion limit in public low voltage distribution system like a class 1. All the 220 volt or 230 volt distribution systems under comes in this category, and the different harmonics as you can see here, like a fifth harmonics typically as a percentage typically of the harmonics, like a all harmonics and permitted like a typically order of 6%. So, you have a complete table for where H is fifth or even harmonics or triple harmonics. So, it is given if you look into corresponding to like all odd harmonics, then the even harmonics and then triple harmonics as a percentage how much can be permitted like also, and it guides about 29th harmonics or so. So, this guide voltage distortion in public low voltage distribution system like. There is another table, certainly voltage distortion limit industrial plant, which is normally little higher voltage, and here also odd harmonics you can see from 5th 7 all odd harmonics and then even harmonics, and then you have a triple harmonics typically percentage harmonic distortion permitted typically for this class 3 equipment we call it like in the commercial applications like. Well, this is about the standard limit which normally we follow couple of standard, and there are many other standard for specific one. These are very general purpose equipment. Then we like to talk about like power quality monitoring. For power quality monitoring, like as we look into, there are lot of now instruments are available like a portable recorder, because you have to go sometime industry or other premises where you look into there is a power quality problem. So, you have to make a measurement and recording. So, these are the some of the power quality, you can call it portable recorder from Fluke Corporation Limited, and you have a similar like 3-phase power quality loggers, then you have a 3-phase power quality recorder, reliable power quality recorder. So, similarly, you have from other like a fixed recorder like 3-phase power analyzer by Norma, reliable power meters like multi-point power recorder. Similarly, you have a other recorder like Fluke 1735 for 3-phase power logger, and Hioki PQ 310094 3-phase power quality analyzer, and then Fluke 434 or 435 for 3-phase power analyzer, and then E-Taker MK2B energy monitor like. Then you have a current clamps which you use for typically for along with those recorder, and you have a current clamp standalone also, as well as AC voltage detector, outdoor visual inspection, and you have a phase sequence indicator also. So, these are the some of the instruments. There are a large number of instruments from different other industry also, like a Yokogawa, or you can call it Hyoki we have written as. Apart from that, there is a typically Agilent. I mean, there are plenty of manufacturers like a Trident, others like So, these instruments are used, or recorders are used to record the power quality problems, because you have to some time for suggesting the right, typically the mitigation technique or mitigation equipment, you have to really make assessment through these recorders that how much is the typically the power quality problem. So, continuous power quality monitoring and detection, recording, and leads to prevention of power quality problem, and power quality monitoring provide a continuous health check of a facility or power system. For example, harmonic interaction between the loads and power conditioning equipment can be spotted, and high ingress current from equipment startup can be detected, and transient from load switching can be seen. And this power quality monitoring may be provided by either the utility or customer or any other person such as energy auditor appointed by typically either industry or the utility like. The power quality monitors must detect and record the types of power quality problems, like they can record like a tangents, which we discussed last time, what kind of a power quality you can call it issues are there in terms of tangent or interruption or voltage sag or under voltage. Voltage sag we defined last time is a short period depression of the voltage, and under voltage means the voltage goes little down for longer period. Similarly, swell, the voltage for very short period goes up and or the over voltage for longer period. Similarly, waveform distortion or voltage fluctuations and frequency variations. So, these are the typically you can call it power quality parameters or which these monitors can monitor it. So, well, coming to like what is the objective of this power quality monitoring? Very purpose is to quantify the power quality phenomena at the particular location of electrical power equipment, and to diagnose to incompatibility between the supply and the consumer loads, and to predict the performance of the load equipment and select power quality mitigation systems for that particular location, and to find out the choice of monitoring equipment, the method of collecting data etc., at particular location like. Well, the IEEE 519 give a big table of parameter which can be determined from this acquired voltage and current data. As you can see here, all these data which we were discussing last time also, like ANSI, transformer derating factor, earth sum power factor, earth sum displacement factor, earth sum voltage ampere current crest factor. We will define time to time, of course, when we will go for numerical problems of current total harmonic distortion, current TID in terms of RMS, and current interharmonic distortion, current TID RMS, current unbalance, displacement power factor, frequency, fundamental. So, all these parameters virtually we look into typically from acquired voltage and current signal which we record it like. So, we can typically either can get from these instruments these data, or we can probably estimate from other data which we are recording like. Well, what is the justification for power quality monitoring? How you can convince really to the industry why we should go to power quality monitoring? The major reason for monitoring the power quality is the financial damages produced by the power quality events in critical and sensitive equipment or in the process or manufacturing industries like. So, power quality problem and event may cause malfunctions of the equipment or process, it can cause the damage, it can cause process interruption and other anomaly in the equipment and their operations. The power quality monitoring needs resources in terms of like equipment, training, education, and of course, the time. Well, some of the following aspects may be used to convince the users for power quality monitoring: find out the need for mitigation of power quality problem, to schedule preventive and predictive maintenance of the plant or the process or the industry, or to ensure the performance of equipment, to assess the sensitivity of the equipment to power quality disturbances, to identify power quality events and the problem, and to reduce the power losses in the process and distribution system, to reduce the loss in production and to improve the equipment availability in a particular process like. So, we would like to discuss some of the typically quantifying some of these quantity through some of the numerical examples, and this is the first example which normally we will refer all these kind of parameters or the variables in when we were talking about the all these power quality problems. So, taking a kind of waveform which is different from sine wave in a square wave of current I of 100 ampere, which you see the waveform like a square wave here. Calculate the Crest factor, distortion factor, all these we will define and then we will calculate, and total harmonic distortion. So, you can just see typically this waveform which is square wave here, and you can see the harmonic spectrum also of it. I mean corresponding to, if 100 ampere is the amplitude of this square wave, then the fundamental certainly in this is typically about 127.3 and total harmonic distortion is 48% like. So, coming to the solution of this, we can say given that a square wave which have amplitude of 100 ampere, the RMS component of a square wave is your I 1 equal to 4 upon pi divided by, you can call it root 2, which becomes 2 root 2 upon pi into I. It is a 0.9 times the amplitude, so it becomes 0.9 I. The RMS value of a square wave, if you take RMS of it, that is I RMS will be equal to same as the amplitude of a square wave, that is I, and the Crest factor of this square wave or any wave, we define the Crest factor equal to peak value divided by the RMS value of a square wave. So, in this case you will just see RMS value as well as peak value is both are equal, that is I. So, it is equal to Crest factor equal to 1. Normally, the sine wave Crest factor is, you can call it in peak value or Crest value is root 2 and times your RMS. So, Crest factor typically is your root 2 means 1.41. So, here it is less than even the sine wave like. So, distortion factor, we define the distortion factor means quantification of all the harmonics typically here. We define as fundamental component of a square wave divided by RMS of the square wave, that is equal to I 1, that is fundamental is I 1 divided by RMS, total RMS. The I 1 is the RMS of the fundamental component and I the RMS of the total square wave. So, this becomes 0.9 I mean like, and total distortion, harmonic distortion of this square wave is equal to under root I RMS square minus I 1 square divided by I 1, and total RMS here it is I. So, that becomes I square minus 0.9 I square divided by 0.9 I. So, I cancel out and you get 0.4843, and if you take in percentage, that is in per unit, so it becomes 48.34%. So, square wave have a total harmonic distortion of 48.34%, and this becomes very important because you will be dealing such quantity or such kind of waveform very frequently into the typically in entire course. So, I mean these are the things which probably may require to you have to keep in mind all the time. So, we come to like another waveform which is also very popular, I mean in square wave, in quasi square wave. Quasi square wave means 120 degree pulse width out of 180 degree. So, duration is only 120 degree pulse width of the current amplitude of I, and if it is has a 100 ampere, which I have taken typically for the convenience, calculate the Crest factor, distortion factor, that we call it DF in short, and total harmonic distortion called TAD. So, in this case if we look into that, you have a quasi square wave which is width of 120 degree, and if you take a harmonic spectrum of it, you have a fundamental let us say 100, but you will see there is no third harmonics in this, I mean because of this nature of the waveform, and you will have a harmonic only order of typically your 5th and 7th. So, harmonics in this case will be like you have a 6 and plus minus 1. So, you will have a after fundamental, you will have a 5th, 7th, then another band will be 11, 13, then 17, 19, that will be the band in total, I mean this kind of harmonic spectrum. So, coming to of course quantitatively to find out typically all these parameters. So, given that a quasi square wave of 120 degree pulse width duration, it has an amplitude of I equal to 100 ampere, and the RMS of the fundamental component of quasi square wave is I equal to again 2 root 2 by pi, which comes out from 4 upon pi divided by root 2 into pulse width like sin 120 by 2. I mean that is sin alpha by 2 virtually. I mean if you derive the formula equal to I, so it becomes root 6 upon pi into I, the amplitude, and the root 6 by pi value is typically 0.7797 I, and the RMS value of quasi square wave, I mean this wave is typically I RMS equal to root 2 by 3 I, virtually it is 120 out of 180 degree, that is why you can call it is 2 by 3 and root of this I. So, it becomes 0.8165 I, and then you can find out the Crest factor, like that is nothing but the typically peak divided by the your RMS value. So, peak is here is I, and your RMS value which we calculated it of total RMS of this waveform is 0.8165 into I. So, this becomes 1.225. So, this is the crest factor. This crest factor is also still less than the sine wave, because crest factor of sine wave is your √2, that is 1.41. And the distortion factor which we define like fundamental RMS value divided by total RMS, and we already find out the fundamental 0.7797 and divide by typically 0.8165, we keep the value, then you get 0.9549. This is also very important, because this waveform in most of the 3-phase circuit, either 3-phase typically control rectifier, or you will have a 3-phase inverter. So, such waveform you will be dealing many times, I mean in your this power quality course or even other courses also of electrical engineering. So, this becomes very important, and the total harmonic distortion in this waveform is your IRMS square minus I1 fundamental current square divided by I1 fundamental current, and this becomes in per unit 0.3108, and if you take a percentage multiplying the 100 to it, become 31.08% like. So, this is the kind of total harmonic distortion of 31.08%. Why this has reduced to 31% from 48%? Because in this case compared to previous square wave, I mean there is no triplan harmonics, either third or ninth harmonics in this waveform. So, all the triplan are eliminated in case of the 3-phase, I mean typically, and that is the reason this reduction in the total harmonic distortion, or you can call it this waveform is going to be more closer to the sine wave like. So, well, taking a typically third example, a 3-phase unbalanced supply system has the following voltage, that is unbalanced voltage in per unit, VA, that is RMS in, you can call it voltage in per unit 0.9 at the angle 0, then another phase 1.05 at the angle of 240, and VC 0.95 at the angle of typically of your minus 120. Just make the correction, I am like. So, find the value, please make the correction here, it is I mean angle minus 120, and find the positive, negative and 0 sequence component of supply voltage. So, in 3-phase unbalanced supply system is having the following voltage, I mean same like VA equal to 0.9, VB 1.05 and VC typically of 0.095 per unit. So, you can find out the 0 sequence from sequence formula, I mean like VA 0 equal to VA plus VB plus VC by 3, and it comes 0.0044 at the angle of minus 139.10 degree in per unit like. As the 0 sequence component of phase B, C is the same, because they are co-phasal. So, the same value will be there for B and C phase 0 sequence component also. Now, you can find out the positive sequence component of phase A can be calculated from VA1, which we normally call forward voltage, or you can call it positive sequence voltage. This comes a VA plus A is VB plus A square VC by 3, where A is the typical operator, I mean of the angle of 120 degree. So, you can keep the value of VA, VB, VC. So, this is the typical A operator, okay. This is typically A square operator, and you keep the value and come out from 0.967 at the angle of 0 degree per unit. So, positive sequence component of the phase voltage of B and C can be calculated, which will be virtually at the angle of 240 and further at 120, and they will also come the same magnitude, but at different angle. So, by this way you are able to find out typically your positive sequence and negative 0 sequence, and we can find out the negative sequence for phase A, that is VA2, that negative sequence we normally denote by 2. So, we call it VA2, that will be equal to VA square plus A square VB plus AVC divided by 3, and if you keep the value of all these, so it comes 0.044 at the angle 139.107 degree per unit, and the negative sequence component for other 2 phases like B and C are can be calculated in the same manner, except you have to put the angle operator corresponding to that, and then it comes out the magnitude will be the same for, because you can define the positive sequence is also a balance, negative sequence also balance, but their angle will be differing like 120 degree. So, you have again 0.044 for B phase as well as for C phase also 0.044 at the angle 19.107 degree per unit like. Coming to another example, the fourth example, a 3-phase unbalanced supply system having a phase voltage equal to VA equal to 1.1 at 0 degree, VB equal to 1.0 per unit at 230 degree, and VC 0.95 at the angle of 120 degree per unit has unbalanced load currents at IA at 0.8 per unit at minus 20 degree per unit, IB 0.6 at 270 degree per unit and IC 0.4 per unit at the angle of 90 degree. To find the total complex power, the positive sequence component of power, negative sequence component of power and the zero sequence component of power. So, given that a 3-phase unbalanced supply system, voltage are already given, we already talk about, and current is also given. So, we can find out total complex power VABC plus J QABC as a VIA conjugate plus VBIB conjugate, VCIC conjugate, and we put the value of this and calculate it, it comes 1.619 per unit at the angle of 3.729 degree. So, this is typically the total complex power. Well, we can calculate the positive sequence component of power from P1 plus JQ1 from the typically positive sequence voltage and conjugate of positive sequence current. So, here we can just put the relation or formula for positive sequence voltage as well as the positive sequence component, and in these formula if we give the value for all this VABC and IABC, and then we get the positive sequence power 1.64 per unit at the angle of 2.85 degree. Similarly, we can find out the negative sequence power P2 plus JQ2 as a again the multiplication of your VA2 positive sequence voltage and as a conjugate of positive sequence your negative sequence current, negative sequence voltage and negative sequence conjugate of current, and we put the value here of the both and calculate. So, it comes the negative sequence typically power comes to 0.021 per unit at the angle of 145.81 degree. Similarly, we can find out the zero sequence power by P0 plus JQ0 again zero sequence voltage and conjugate of zero sequence current multiplying it, and just we put the value. So, it comes 0.18 per unit at the angle of 139.63. So, it means that the total complex power is equal to the sum of all three sequence component power. So, if we what we got in previous case, so we got VABC plus JQC, we put all the value and we just put the same follow. So, it comes like 1.619 per unit at the angle of 3.729, which we calculate by another alternate method in previous slide also. Then coming to this is just to introduce you typically about the power relation. In case of the power quality issues when like here the voltage and current was unbalanced. This is another example in 3-phase AC system, there is a voltage sag at the point of common coupling of 15%, 25%, 35% on 3 phases for 10, 15 and 20 cycle respectively. Calculate the rate addition sag score and B voltage sag lost energy index which define Vs LEI of this sag event. So, given the 3-phase AC means there is a voltage sag at PCC and it results the voltage magnitude which is given already 15% res means V1 is 0.85 per unit, V2 0.75 per unit and V3 0.65 per unit, and for the T1 that is 10 cycle of 20 millisecond means 200 millisecond and 15 cycle of again 20 millisecond 300 millisecond, and T3 typically of 20 cycle of 20 millisecond becomes 400 millisecond, and quantifying the sag for retrograde addition sag score has a list one phase equal to or below 0.75 per unit. So, retrograde addition sag can be calculated like SS equal to VA plus VB plus VC by 3, and if you put the value, so it comes 0.75, and voltage sag lost energy index from this event can be calculated like VLSI by putting this relation 1 minus V upon V norm e power 3.14 into TA plus 1 minus VB upon V norm again 3.14 and TB, and similarly 1 minus VC V norm 3.14 TC. So, if you put the value it comes 19.184 as a voltage sag lost or VSLEI, like just to introduce these terms related to. So, coming to another example, a single phase transformer used to feed a single phase diode bridge rectifier with a constant DC load current of 90 ampere, and transformer has been rated for a winding eddy current loss density of 5%, that is 0.05 per unit, and calculate the derating factor. So, it means we are typically having a non-sinusoidal current in the transformer. So, transformer have to be typically derated in that we have to find out how much is the derating of the transformer. So, in single phase rectifier the supply RMS current that is IS equal to I0 that is about 90 ampere, and because it is a kind of like a square wave the supply current will be, if it is a 90 ampere is the constant current at the diode rectifier output, I mean this condition can be only when you have very high inductance in like a single after single phase diode rectifier. So, you will have a square wave in the supply current. So, harmonic present in the current are like third, fifth, all the odd harmonics like a third, fifth, 7, 9 other than fundamental, I mean this will be all odd harmonics 11 and so far. So, maximum rated eddy current loss here PEC R will be in per unit 0.05, which is already given there, and given maximum load current loss density, that is PLL R per unit, is 1.05, that is 1.05 per unit, and we can find out typically the stress is loss, I mean IH upon I1 square, that is 1. So, all the harmonics we take into account like 1 square plus 1 by 3 third harmonic, fifth harmonic, 7th harmonic up to 11th harmonic. So, it becomes 1.1921. Similarly, we can find out along with the harmonics order square. So, if we put the value, that comes around 6, and we can find out the harmonic loss factor from the relation of H, this IH upon I1 square into H square. So, if we divide by the factor of IH upon I1 square, summation of all harmonics. So, 6 by this. So, it comes like a 5.033 for all the harmonics 135,979, and I max per unit, that is under root PLL R per unit divided by 1 plus F H L, by which it is supposed to be derated PEC R per unit, and if you put the value, it comes 0.916. So, the derating factor is the estimated order of 91.59% or 0.196 per unit. It means, if such a current is flowing into the transformer, then you are derating typically around 9.4, typically 8.4% in the transformer. So, it converter shown here below is supplied from AC supply of 220 volt 50 hertz at the fire angle of thyristor alpha equal to 60 degree. Consider the continuous load current of 10 ampere, compute the total harmonic distortion of the AC mains current, distortion index din of the AC current, and total demand distortion, I mean TDD of AC mains current, distortion factor, displacement factor, and power factor. You can see this thyristor converter with the highly inductive load can cause this constant current, like if it is output is the fixed current, this is supply voltage, this is the constant current, then this will be the current of like your square wave, but shifted by fire angle 90 degree, because the thyristor is allowed to conduct from here, but it will be square, and next cycle again it will come starting from alpha your 60 degree. So, it will be shifted by 60 degree, but a square waveform like or so. So, with this waveform, of course, we can make a calculation of all the parameters which has been asked in the problem. So, given that supply voltage Vs equal to 220 volt and frequency of supply 50 hertz, and the DC current IDC on the load current is 10 ampere and fire angle is 60 degree. So, in single phase thyristor bridge converter, the waveform of the supply current is a square wave with the amplitude of DC link current. Moreover, the RMS of fundamental square wave we already discussed in the previous problem, that is 0.9 times the amplitude of it. Therefore, IS equal to I0 equal to 10 ampere, and IS1, that is fundamental, equal to 0.9, I0 equal to 9 ampere. So, total harmonic distortion TAD of AC mains current can be found out from under root RMS, total RMS square minus fundamental RMS square divided by fundamental RMS, and that comes 48.4843, and that becomes 48.43%, and total distortion index of the AC mains current equal to TAD upon 1 plus TAD square. So, if you put the value, then it comes 43.59%, and total demand distortion of AC mains current equal to total current demand distortion. Calculate the harmonic current distortion against the full load demand level of the electrical data, and that is at full load equal to TDI equal to TADI equal to 48.43%. Like. Therefore, TD give us better insight about how big is the impact of the harmonic distortion in the system. For example, one could have very high TAD, but the load of the system is low. So, in this case, impact of the system is low, and distortion factor DF is equal to 1 upon 1 plus TAD square. That relation also you have to really derive or remember it, equal to IS1 upon IS and equal to 0.90, and displacement factor, that we call it the fundamental power factor. I mean, if you have a sine wave, what is the power factor? That is cos theta 1, where theta 1 is the angle between the fundamental voltage and fundamental current, that is here equal to the fire angle, that is cos alpha, and it is equal to 60 degree equal to 0.5, and the power factor, that is equal to displacement factor multiplied the distortion factor, it is equal to 0.9 into 0.5, which comes around 0.45. Like so, this gives all the data there. Now, we will consider of course, some kind of other kind of nonlinear load also, or which draws the distorted waveform and find out all these parameters like. So, this is interesting example, a single phase AC controller shown in figure 2.13 having a heating load resistive element of 10 ampere. The input voltage is 220 volt RMS at 50 hertz. The delay angle of thyristor is alpha equal to 120 degree. Feeder conductor have a resistance order of RS equal to 0.1 ohms each, and calculate the AC RMS current, the losses in the distribution system. If an ideal shunt compensator is used to compensate the power factor to unity of this load, then calculate the AC RMS source RMS current, and then losses in the distribution system and ratio of the losses in distribution system without and with compensator. So, what we are saying here, I mean in parallel to this we will be putting compensator which will make this current sinusoidal as well as typically the reactive power of it also supposed to compensate. I mean, so we have to just find out like how, what will the typically the the data there. So, given that supply voltage equal to Vs equal to RMS 220 volt, frequency of supply 50 hertz, and R resistance equal to 10 ohm, and the feeder resistance is 0.1 ohm, and firing angle is of alpha equal to 120 degree. So, total resistance of the circuit will be R load resistance plus 2 RS, means of 2 feeder, 1 return and 1. So, it will be 10.2 ohms. So, in single phase system, the phase controlled AC controller which you see in the figure, the waveform of supply current has a value of Vs upon RT from firing angle to the angle of 180 degree or pi. So, it will become like a 220 your root into root 2. So, it becomes peak value will be your 331.13. The supply RMS current Is equal to Vsm in bracket your this formula, I mean which available in most of the typically of your power electronics book, 1 upon 2 pi, and in the bracket pi minus alpha plus sin 2 alpha by 2. So, this is typically the RMS voltage divided by RT of RMS of this typically waveform. If you talk about the voltage, and then it comes 9.537 ampere, and active power of the load which is this current square multiplied the resistance of the load. So, it becomes 909.482 watt. So, that is the power, that is the RMS current. Well, we can find out the losses in distribution system can be calculated, P loss equal to 2 I square RMS current square multiply the resistance of the feeder, because there are two let us say cable 1 coming for going. So, that is why we have to take a factor of 2. So, 2 into 9.537 square into 0.1. So, it becomes 18.19 watt. So, after the compensation, the power factor is to be corrected to unity of the AC mains by shunt compensator, and the current in AC mains becomes sinusoidal in phase with that of supply voltage. So, new supply current is as a RMS fundamental active power component of load current, that is Is equal to Is1A, that is nothing but active power which is consumed by this system PL upon Vs, and this total power is your 909 watt divided by 482 divided by 220. So, the RMS current becomes like 4.134 ampere. So, losses in the distribution system, you can just see earlier the current was typically of your 9.537, but after compensation current has reduced to 4.134 ampere, and the losses in the distribution system are calculated as P loss equal to 2 ISC square into RS, new ISC square virtually into RS, that is given a notation after the putting a compensator, and 2 into 4.134 square into 0.1. So, it becomes 3.418 watt, which is reduced from 18.19 watt to 3.41 watt. So, ratio of the losses without and with compensator is typically 18.19 watt divided by 3.41 watt. So, it becomes 5.322. So, it means that the such nonlinear load causes increased losses in the distribution system manifold as much as 5.322 times if you have a like typically along with the compensator like that. Of course, we will talk about compensator little later. I mean like these are also very interesting practical example problems. I mean you can see in this figure a single phase AC voltage controller shown in figure below is used to control the heating of packing element in a food vending machine at a power of 100 watt at 10 volt fed from single phase AC mains of 230 volt 50 hertz. The feeder conductor have a resistance of 0.2 ohms each. Calculate the AC source RMS current. losses in the distribution system. If ideal shunt compensator is used to compensate power factor to unity, then calculate the AC source RMS current, then losses in the distribution system and rest of the losses in distribution system with and without and with compensator. You can just see the kind of, typically it is a practical example. You might have seen the food packing machine typically of having a heating element, or the sweet packing machines like. Well, coming to the solution, given that the supply voltage Vs equal to 230 and frequency is 50 hertz, the power is 100 watt and resistance is 0.2 ohms, the load resistance RL equal to Vs square by P. So, here the voltage, I mean typically across the load is only 10 volt, 10 square by 100. So, it becomes like a power is 100 watt. So, it is only 1 ohm, and the RMS voltage across the load is typically Is into RL equal to 10 volt, and the supply current now will be PL upon RL. So, it is like a 10 ampere VLS upon RL, and the losses in the distribution system are calculated like 2 Is square RS 2 into 10 square into 0.2, that becomes like a 40 watt. So, after the compensation you can say the load is like 100 watt, but the losses is 40 watt because of this non sinusoidal current. Like after the compensation, the power factor is corrected to unity of AC mains by a shunt compensator, and current in the AC mains current becomes the sinusoidal in phase with that of phase voltage. So, new supply current is a RMS fundamental active component of current, that is Is equal to Is1 P upon Vs, that is 100 watt is the load power divided by 230. So, current is only 0.43 ampere, and the losses in the distribution system are calculated as 2 Is square Rs. So, that is 2 into 0.435 square into 0.2. The loss is 0.076 watt. So, ratio of the losses without and with compensator is 40 divided by 0.06. So, it is 539. So, it means that the such a nonlinear load cause increased losses in the distribution manifold such as 529 times like. So, that is the impact of such nonlinear load. You have to use cautiously. What is the right solution? Because we want here typically the voltage across the load only 10 volt and for 230 volt supply. So, what the suggestion you suggest, like there can be a good suggestion that you can typically take a kind of a transformer which reduces the voltage from 230 to typically order of like a 23 volt 1 to 10 transformer, and then you can control this. So, you will improve the typically the power factor also, and supply current will reduce because of this step down transformer. Well, coming to another example, typically a single phase uncontrolled bridge converter shown here in figure below has a RE load equal to 2 ohm and the you can call it battery voltage of 275 volt. The input AC voltage is Vs equal to 220 volt RMS at 50 hertz. The feeder conductors have the resistance order of 0.1 ohms each. Calculate the AC RMS current, losses in the distribution system, total harmonic distortion in current, and Crest factor of supply current. If the ideal shunt compensator is used to compensate power factor to unity, then the calculate the AC source RMS current, losses in the distribution system, ratio of the losses in distribution system without and with compensator. So, you can clearly see typically the circuit with the diode rectifier, and the load is having resistance with the typically the battery voltage, and the kind of current in 2 half cycle, because of the polarity of unidirectional, you will get a current only flowing when supply voltage is more than the battery voltage. So, that is why you will get only the 2 segment of current here, and when it gets reflected into AC supply, you will have a positive half cycle, negative half cycle with the angle conducting from alpha degree to beta degree, and alpha is decided by when your supply voltage is going to be more than your typically battery voltage of 275, and similarly for negative portion also. So, you can see this is a discontinuous current. So, we can typically find out the values of and it will have a substantial order of harmonics into it like. So, given that the supply voltage 220 volt and the peak value of this will be like a root 2 into 220, that is 311.13 volt, and frequency 50 hertz, load resistance around 2 ohm in series with the battery voltage of 275 volt, that is E. So, in single phase diode rectifier with the RE load, the current flows from angle alpha when AC voltage equal to the battery voltage E and to the beta, at which the AC voltage again reduces to value of E. So, we can find out from this the value of the typically the total resistance of the circuit 2 Rs plus R, that is 2 into 0.1 plus 2, that is 2.2 ohm, and the alpha angle can be find out from the relation when your sin Vsm sin omega t equal to E. So, from this relation you can find out alpha, and this becomes sin inverse E upon Vsm, and that comes around 62.11 degree. Similarly, beta also can be find out your pi minus alpha because of the symmetry. So, it comes 117.89 degree. So, conduction angle here beta minus alpha, that is only 55.78. It means out of 180 degree you will get a conduction or supply current only for 50.78 degree, and the active power drawn from the AC mains will be like a P equal to I s square R t plus I E I 0, I mean which is charging the battery, and this comes like typically like your 194.99 if you put the value, and 1858.39 if you put value of E and I 0, which we already calculated, and it comes 1026.936 watt. So, fundamental RMS current from AC mains will be your IS11 P upon Vs. If we consider this is only the typically a sine wave, so it becomes like 1026.936 divided by 220. So, current is 4.668 ampere, and supply AC peak current is typically VSM minus E, where the let us say voltage battery voltage is subtracted divided by RT. So, it becomes 16.43 ampere. So, load average current you can calculate from the relation here from that waveform 1 upon 2 pi RT to VSM cos alpha plus 2 E alpha minus pi E, that is 3.38. Now, you can typically find out the parameters from this, the RMS of supply current of this discontinuous current of AC mains from this relation, I mean 1 minus pi RT square, and then in bracket 0.5 VSM I square plus E square into pi minus 2 alpha plus 0.5 VSM square sin 2 alpha minus 4 VSM E cos alpha. You will find this relation certainly in many power electronics book, the derivation of it, or you can derive the relation. So, it comes equal to 6.655 ampere, and losses in the distribution system are calculated as PL equal to 2 IS square RS, that is 2 into that RMS current typically into 0.05. So, it comes 8.85, and TAD of the current is typically, if you put the value here, it comes like a TAD comes around 101.61%. So, you can see this total harmonic distortion is order of your more than 100%. So, such a distortion is there such a waveform, because it is only conducting for less than 60 degree, and Crest factor of supply current peak upon RMS value, that is 16.421 divided by 6.655 2.46 ampere. After the compensation, the power factor is corrected to unity of AC mains by shunt compensator, and current AC mains current becomes the sinusoidal in phase with the phase voltage, and new supply current is an RMS fundamental active component of current after the compensation IS equal to IS1 P upon Vs, and you can find out P upon Vs, that power divided by your RMS voltage 4.661, and losses in the distribution system is 2 IC square to RS equal to 4.6 into 0.1. So, it is 4.358 watt, and then we can find out the ratio of the losses with or without and with compensator, P loss upon P loss SC after the compensator. So, 8.858 divided by 4.3, so 2.033. It means that the such nonlinear load caused the increased losses in the distribution system manifold as much as 2.033 times, like I mean that causes the problem in distribution by increasing the losses like. Yeah, coming to another example, in a 3-phase system, the line voltage of 415 volt 50 Hz 4 watt distribution system, 3 single phase load connected between phase and neutral, as you see this figure, having a single phase thyristor bridge converter drawing a equal current of 12 ampere constant DC current at 60 degree fire angle of its thyristors shown here in figure, and feeders and neutral conductor have the resistance of order of 0.2 ohms each. Calculate the AC source RMS current, neutral current, losses in the distribution system, and if an ideal 4 wire shunt compensator is used to compensate the power factor to unity in each phase, then calculate the AC supply RMS current, neutral current, and losses in the distribution system, and the ratio of losses in distribution system without and with compensator. So, you can see the kind of circuit that you have a load RL load, and these are drawing the current like typically like a square wave current, constant current of I 0, and the current on this side will be a square wave I, as you can see the 3 phase supply voltage and 3 phase current of a square wave shifted by 120 degree, and this is the neutral current. If you make a sum of all 3 current, neutral current is also a kind of a square wave, but the 3 times the frequency, like because tuple harmonics will flow into the neutral. So, you can clearly see the 3 phase equal balance current, but of course, not sinusoidal square wave current, cause the neutral current equal to the phase current, and this is of course, the typical output voltage of one phase and load current of one phase like. So, this is very important, we like to analyze of course, in the result about the neutral current and this one like. So, coming to the solution, given that supply voltage of equal to Vs equal to 415 by root 3 V equal to 239.6 volt and frequency of supply 50 hertz, RS equal to 0.2 ohms and DC link current of 12 ampere with a firing angle of 60 degree. So, in single phase thyristor bridge converter, the waveform of supply current is a square wave with the amplitude of DC link current. So, AC RMS current is same as the your DC current, that is because of square wave. So, it is IS equal to I0 equal to 12 ampere and the neutral current you have seen is the same of the same peak, but 3 times the frequency of your this square wave. So, it also 12 ampere and since it will also be a square wave at 3 times the fundamental frequency, because triple harmonics will flow into the neutral, and losses are now in distribution system is 3 times in all 3 phases 3 IS square into RS plus the neutral current IS square RS. So, you will have a 3 times 12 ampere into 0.2 and 12 ampere square 0.2, that is the neutral current losses, and it becomes 115.2 watt. So, after the compensation, power factor corrected to unity of AC mains current by a 4 wire compensator, shunt compensator, and the 3 phase currents in AC mains current become sinusoidal in phase with their respective phase voltage, and neutral current becomes 0 like. So, the new supply current is the RMS active component of current only, IS equal to IS 1A, that is only fundamental current, which is equal to active component of fundamental current, which is nothing but IS 1 cos alpha, and that is nothing but 12 into 0.9 into cos alpha cos 60 degree, that becomes 5.4 ampere. So, in this case after the compensation, since the 3 phase currents in the AC mains are balanced and sinusoidal, therefore, neutral current becomes 0. So, ISNC after compensation is 0.0 and losses in the distribution system, now you can find out typically 3 ISC square into plus ISN square into RS. So, typically current here is 0. So, this will become 0 and this is 3 into 5.4 square into 0.2. So, it becomes like a 17.496 watt. So, ratio of the losses without and with compensator is like a P loss divided by P loss with the compensator, and 115.2 divided by 17.496. So, it is 6.584. So, it means that such a nonlinear load cause the increased losses in the distribution system manifold such as 6.584 times, like that is the effect of nonlinear load on the distribution system. Coming to another example, typically how it affects really the performance of your like a induction motor we were talking about in last lecture. A 3 phase 11 kilowatt, that is 15 horsepower virtually 450 Hz 4 pole data connected squirrel cage induction motor is used to drive a compensator load of a constant torque. It runs at 3% slip at full load and rated voltage and frequency. If terminal voltage reduces to 370 volt, calculates its slip speed, shaft speed, output power, rotor winding loss and the ratio of rated rotor winding loss at rated voltage. Consider the small slip approximation. So, given that a 3 phase 11 kilowatt 415 volt 50 hertz 4 pole data connected squirrel cage induction motor is used to drive the compressor of constant torque, it runs 3% slip at full load and rated voltage and terminal voltage 370. So, for a small slip approximation we can find out slip is inversely proportional to voltage square, and new slip at reduced voltage you can calculate from this voltage relation. So, it comes like a 3.774%, like in place of 3% it increases to 3.774% like. So, synchronous speed you can calculate 120 f, that is 120 f by number of pole like a 1500, and the shaft speed reduced typically because of this reduction of the voltage 1 minus slip s. So, it becomes 1443.388 rpm. So, output power at reduced voltage at a constant torque is H p equal to omega m into T m, you can put the typical value. So, it comes like typically 10.912 kilowatt because of the constant torque load T equal to P g upon omega m s, air gap power upon synchronous speed, therefore, P g is constant. So, the rotor winding loss at reduced voltage will be equal to P r W n into S n P g. So, those loss will increase S n upon S into P r W r. So, that will be so it increased 1.258 times the previous losses. So, it can be concluded that the decrease in the terminal voltage results in increase in the rotor winding losses. However, a decrease in terminal voltage at a constant frequency decreases its core loss and magnetizing current, which partly offset its effect like now. So, another example, a 3 phase 11 kilowatt 415 volt 50 hertz 4 pole data connected squirrel cage motor is used to drive a compressor load of constant torque. It runs 3% slip at full load and rated voltage and frequency. If terminal voltage increases to 450 volt, calculate the slip, shaft speed, output power, rotor winding loss and ratio of watt loss to this. Consider a small slip approximation. So, we calculate that this motor of 11 kilowatt 415 volt 4 connected squirrel cage motor is used to drive the compressor load of constant torque and runs at 3% slip at full load and rated voltage and rated frequency. A terminal voltage is 450 volt. So, for a small slip approximation, again slip is proportional to 1 upon V square. So, new slip you can calculate, it reduces to from 3% to typically 2.511% and synchronous speed you can find out, and then the rotary speed you can just find out because of this increase in voltage, it comes 1461.72 volt like. So, the output power at increased voltage at constant torque, I mean you can find out this typical value with the corresponding to the slip. So, it comes 11.051 kilowatt, and because of the constant torque T equal to Pg upon omega ms, the air gap power upon synchronous, therefore, Pg is constant. So, the rotor winding loss at this voltage is equal to. So, this typically comes to little reduction into that because of a decrease in the slip 0.085. It means it can be concluded that the increase in terminal voltage results in a decrease of rotor winding loss. However, an increase in the terminal voltage at constant frequency increases the core loss and magnetizing current, which partly offset its effect like. So, we like to summarize this, I mean what we covered today. The exhaustive exposure of the standards, definitions, monitoring and assessment of power quality are to be beneficial for power quality improvement to the designers, users and manufacturer and research engineers, and of course, these are the some of the references like. So, we like to typically conclude this lecture, and thank you very much.